Well, I'd like to thank Maya for her introductory remarks and Stephen and Mark for a challenging talk. Uh, I have some studying to do, that's for sure. Uh, it, it is a truth universally acknowledged that humans cannot visualize the fourth dimension, though many have tried, and the mental health facilities and colleges are filled with rambling wrecks who lost their minds in the attempt. There are just three dimensions in plain old 3D. Why create a 4D controller? It's a new way to explore multidimensional space. This is primarily a tool for artists, so the way I'm looking at it, to explore a new degree of freedom. There are two ways to use the controller: as a microscope to look at 4D objects, and like a viewer to see the 3D space all around us, navigating and finding new paths. We're going to examine a three sphere, an object that lives in a four-dimensional space, and then visit its shadow in a WebXR session where you will be able to watch the three sphere rotate in an imaginary plane. It won't be quite hands-on. I didn't quite get the Unity UI system perfected, but I think that it is quite a sight. So get your VR headset ready. This is Ivan Sutherland's original head-mounted display using the technology of 1968. He realized the essential element of VR. He says, although stereo presentation is important to the three-dimensional illusion, it is less important than the change that takes place in the image when the observer moves his head. The image presented by the three-dimensional display must change in exactly the same way that the image of a real object would change for similar motions of the user's head. Sutherland realized that it is the mobility of the observer that is the crucial feature of VR, a term that hadn't been invented yet. This is the mobile binocular observer. Rudy Rucker, computer scientist and science fiction writer with a special interest in the concept of four spatial dimensions, says, what shall we call the two regions of hyperspace? Charles Hinton, a 19th century explorer of 4D, has suggested the words ana and kata to be used more or less like the words up and down. Just to have something to think about, we might think of heaven as lying ana above our space and hell as lying kata below. A 4D angel expelled from heaven would tumble through our space like a man falling through flatland, an exciting moment of grotesque, incomprehensible cross sections, splitting and merging and falling about. This is a schematic for a 4D controller. This is meant to be designed and built. In white are the components of the classical Cartesian Euclidean familiar space we build our houses in. The fourth dimension, which I have labeled W, is another spatial dimension of this kind, perpendicular to the other three. This dimension doesn't exist, so I've indicated that it is imaginary by drawing it in cyan, the color of the luminiferous ether, I think. These are all spatial dimensions. Each axis is mutually perpendicular to the others. Time ticks along as usual, so the 4D system is embedded in a 5D space, including time. The white sphere labeled 1 is a scalar. It has only radius with no orientation or position. It is at the origin of the system. It is a 4D cross-section of a sphere of boundless dimensions. If you decrease the radius of the scalar, all the other objects decrease proportionally. XYZW is called the pseudoscalar of this space. It is a three-sphere, an object that lives in 4D space. The pseudoscalar has the same magnitude as the scalar, but with the structure inside. It is the largest structure that can be built in 4D space and has the magnitude of 1. It has 1 degree of freedom. X, Y, and Z are vectors with an orientation and a magnitude. They are controlled by sliders. Each vector has a magnitude of 1/4 in the initial condition, so the magnitude sum to 1. Adjusting the magnitude of one vector causes the other vectors to compensate, so as to maintain the sum of the magnitudes of 1, which means that the vector's head lies on the surface of the 3-sphere. This is called unitary evolution and is very important in physics. The W vector intersects plain old 3D at the origin, so it has one real point drawn in white. YZW, ZXW, XYW, and XYZ are the pseudovectors of 4D space. They are the surface of balls controlled by a trackball. The trackball has latitude and longitude, so two numbers can locate a point on the surface, but the point has 3 dimensions in space. The X vector is perpendicular to the YZW sphere. The surface of the 2-sphere is 2-dimensional, but it is embedded in 3 space, analogous to the 3-sphere being embedded in 4 space, or the line being embedded in 2 space. So turning the dial changes the magnitude of 2 of the X, Y, Z, and W vectors. The rest remain the same value. The middle row contains the 6 bivectors of 4D space. Each of them is a circle, a 1-sphere, embedded in the 6 different 2 spaces. One number can identify a position on the circle. One of the differences between 3D and 2D is that in 2D, 2 planes can meet at only one point, like X, Y, and ZW. They therefore can rotate independently while maintaining a rigid 3-sphere. These pairs of bivectors are called Clifford rotations. All vectors are multiples of this vector. The proportions of colors are different, and the vector points in a different direction, but they're related. The bottom hemisphere could contain vectors of the subtractive colors plus red pointing down, probably should be at right angles to the heavenly vector. And this is 1/4 this is 1/4 X, 1/4 Y, oops, sorry. 1/4 Y, 1/4 Z, and 1/4 W. And so if you look, you can go half in this direction, half in this direction, half in this direction, and then half in this direction to end up on the surface sphere. So all right, yeah, all right, just a sec. I've lost my thing here, just a moment. These are the 6 bivectors. The yellow is made up of red and green, the red x-axis and the green y-axis. And this is actually a bivector that's extends into the w-axis, and it has this part in the r space, in the XYZ space. If you notice, all of these are the w-axis is perpendicular to all of these, so it shrinks it down to a line. This is a stereosphere. This is the shadow of the 3rd dimension here, but this enables you to see what the some of the shapes. There's a lot of the same shapes in 4D when you see that, but it's a stereographic projection that comes from here, goes through one of these points, and then lands on one of these points somewhere. Let's say from here down to here, it would this point is the shadow of this point is this point, and all those points are the shadows. You can see that the shadow actually extends to infinity all the way out to the horizon there. And it's very, very simple transformation. It's just you divide by 1 minus the W axis. And it's the same thing in 4 space, except, oh, this is 4 space. Actually, this is 4 space, this is 3 space. Oops, all right. These are supports for the 4 trackballs, and it's a tetrahedral sort of support. These are designs for the trackball. I want to avoid suggesting a preferred axis of rotation. The trackball has no gyroscopic forces and can move in any direction. The 4 points of the tetrahedron for the sphere is 3D space and allow maximal access to the surface. So the idea is as you're using it, the brackets don't get in the way. The sphere can have information projected onto it by the XR system. The projection can show the surface spinning in 2 different directions. The sphere can even have interior details projected into the interior, like a goldfish in a gold bowl. The projectors are located on the celestial sphere. The 4th dimension is all around you. As SIGGRAPH of Modest Mouse has noted, the stars are projectors, yeah, projecting our life down to this planet Earth. The stars are projectors, yeah, projecting our minds down to this planet Earth. And next I'm going to go to Unity, and we can look at the best way to look at the thing. So this is a 4D sphere right now.
Mike, I just wanted to ask you, did you post the site, the URL in the chat?
I did several times. Yeah.
Okay.
And I think Sunil did. If anybody wants it, let me know, because it's much better. The problem is 4D things do look just like tangles of lines on a plane, but when you see them in virtual reality, it's like magic. At least to me, I'm just blown away by how powerful it looks. Let's see, what did I want to do? I wanted to turn that off. So these are the subtractive colors, and they're on the let's see, they're we have yellow is XY is yellow, cyan is YZ, and magenta is ZX. So these are all the real looking these are all the axes that are real. And if we turn it on, it's wait, my turner oner thing is just a minute. Let's see, now I got to figure out how to get the, how can I get, I want a control that's behind this.
You mean with Google Slides?
No, I want to turn on the animation for the.
Okay, so you stop sharing the screen and then
I'll stop sharing. Yeah.
Yeah, and share your video instead. Okay.
Okay. Now I can go to.
You share again and.
Yeah, I'm going to do that. I'm going to just make this smaller.
Go to advanced or.
Now I'm back here. Okay. Okay, am I back? So we have this.
Yes.
This control right here. So this is one of the, this is a 3-dimensional, this has XY, this is all in XYZ. except it's the shadow, but I'm rotating the the XY plane, for instance, around the XW or in the XW plane. And then the other one we have is turn on the additive. These are the additive ones. This is the simpler to understand. It's really, if you get a chance to see it in 3D, it really makes a big difference. But you can see this just kind of amazes me that this is rotating out in space like that with X and Y, and it seems like there should be a reason that this has the extra. It also has a plane here that's I think this one right here, that it's superimposed, or one on top of the other. So this has a sphere that covers up the blue and the green. It just seems like what my idea is that if you look at this and think about it, and you can start to figure out what's going on, and you can learn to intuit what happens in 4D. Not from a flat screen, I don't think you can do it as easily, but when you see it in VR projected, I find it compelling. I'd like to know if other people do as well. But well, that's I guess the end of the talk here. Let me see if anybody has any questions or anything. Or I guess we're going to have questions after. Yeah.
Yeah, okay. With everybody. I'm just reposting the site information so people can visit it.
Okay.
Oops, I just reposted it directly to Sunil, so now I'll repost it to everybody.
Okay. Let's see. I've got actually one more, and here's the our title for discussion.
Oh, great.
And this I want to put in VR as well. I think it'd look really great. It's the geometric algebra bivectors and points and things, you know. And let's see. Here's something I'd like to put in VR as well. They say here spherically symmetrical collapse. This is Roger Penrose's Nobel Prize winning paper, and they say it's a spherically symmetrical collapse, one space dimension suppressed. Well, we don't have to suppress any space dimensions. We should make a model of this and add that dimension back. What he says is that this disk right here is a flat disk, but it really should be a sphere. So it'd be interesting to see.